Assalamu alaikum. This is lecture 18 of data security and encryption, and in this lecture we are going to continue our discussion about random bit generations, and we are going to implement random bit generations in stream ciphers. So as said, in this lecture we are going to discuss about stream ciphers, and one of the most popular algorithm of the stream ciphers is named as RC4. And in the stream ciphers we will generate with the stream of the bits, and in this algorithm there is a stream generation process which will be taken care with the initialization of a set S, and then there will be some strengths of the RC4 algorithm, and finally we will conclude this lecture with the discussion of true random number generators. We will briefly discuss the concepts discussed in the last lecture about the random bit generations, and the most important topics of the discussed in the last two lectures were entropy sources and the comparison of pseudo random number generators and true random number generators. Then there will be two tests called the conditioning test and health test. We will also discuss in this lecture, and to conclude it we will present Intel digital random number generator mechanism and its implementation details. So as discussed earlier many times, that a typical stream cipher encrypts the plain text one byte at a time. On the other hand, the block cipher uh, encrypts one block at a time, and the block can be about 1 byte or 128 bits as discussed in the AES stream cipher, and 64 bits in the data encryption standard cipher. So although a stream cipher may be designed to operate on a 1 bit at a time or a units larger than a 1 byte at a time, so this figure shows a representative diagram of stream cipher structure. So in this structure, a key is input as depicted on the top of the page. A key is input to a pseudo-random bit generator that produces a stream of 8-bit numbers. The output generator, often called a key stream generator, is combined 1 byte at a time with the plain text byte stream named as M, and it is a bitwise exclusive OR operation with the key K and the message M, and the encryption results in a ciphertext which is depicted here, ciphertext byte stream C. On the other hand, the decryption algorithm works with the same way, and the key is input to the pseudo-random byte number generator, and a key stream is generated which is embedded or bitwise XORed with the ciphertext to produce the original text. For example, if any of the next byte generated by the key stream generator is 1100, for example in this case we take only 4 bits, and the plain text is the same as the key which is also 100, so key is referred as K and plain text is referred as M. So if you perform the bitwise exclusive OR, the final result will be 0 because all the bits are same. On the opposite hand, if you apply the reverse operation, you have the ciphertext now which is equal to 000, and the value is depicted as C, and you embed it with the value of key, which was similar here, and you perform the exclusive OR operator to get the original text back. So the key stream cipher is similar to another algorithm discussed in the previous lecture known as one-time pad. So the difference is that the one-time pad uses a genuine random number stream, whereas the stream cipher uses a pseudo-random number stream. However, following important design consideration for a stream cipher must be taken care of. First of all, the encryption sequence should have a large period. So it states that a pseudo-random number generator uses a function that produces a deterministic stream of bits that eventually repeats. So if we have the longer the period of the repeat, the more difficult it will be to perform the cryptanalysis. This is essentially the same consideration that was discussed with reference to the Winier ciphers, and namely that the longer the keyword, it is the more difficult for an attacker to guess the keyword. Secondly, the key stream should be approximate the properties of a true random number stream as close as possible. So there should be an approximately equal number of zeros and equal number of ones. So if the key stream is treated as a stream of bytes, then all of the 256 possible byte values should appear approximately equally often. So the more random appearing the key stream is, the more randomized the ciphertext is, making it difficult for the attackers. Additionally, the key uh, length of at least 128 bit is desirable in the stream cipher design algorithms. The output of pseudo-random number generator is conditioned on the value of input key. The same consideration that apply to the block ciphers are also valid. So with a properly designed pseudo-random number generator, a stream cipher can be as secure as a block cipher of comparable key length. However, a potential advantage in this case is that the stream ciphers that do not use the block ciphers as the building blocks are typically faster and use less code than a block cipher. So for example, the algorithm discussed next, named as RC4, can be implemented in just few lines of code. Additionally, in recent years, this advantage has diminished a little bit with the introduction of advanced encryption standards, which is quite efficient in software. Furthermore, hardware acceleration techniques are now available for the advanced encryption standard. For example, the Intel Advanced Encryption Standard instruction set has machine instructions for one round of encryption and for the one round of decryption and generation of keys. One advantage of block cipher is that you can reuse the keys. In contrast, if two plain text are encrypted with the same key using a stream cipher, then the cryptanalysis is often quite simple. So if two stream cipher text are XOR together, like we discussed in the last slide, the result is the XOR of the original plain text. So if the plain text or the text string or credit card numbers or other types of byte streams with known properties, then the attacker may be very successful. For applications that require encryption or decryption of stream of data, such as over the data communication channels or a browser using a web link, a stream cipher might be a better choice. For applications that deal with the blocks of data, such as a file transfer, email, and a database, block cipher may be more appropriate. However, either type of cipher can be used virtually with any application. However, in this lecture, we will look at the stream ciphers that use the pseudo-random number generators designed specifically for the stream ciphers. One of the famous stream cipher algorithm is named as RC4, and it was designed by Ron Rivest in 1987 for RSA security. So it uses a variable key size stream cipher with a byte oriented operation, and it is based on the use of a random permutation. So in this case you can use 8 to 16 machine operations that are required per output byte, and the cipher can be expected to run very quickly in the software. RC4 is used in secure socket layer SSL and transport layer security TLS standards that have been defined for communication between web browsers and servers. It is also used in the wired equivalent privacy protocol and the newer Wi-Fi protocol access WPA that are part of IEEE 802.11 wireless LAN standard. So RC4 was kept as a trade secret by RSA Security. However, in September 1994, someone posted the algorithm over the internet, which made it very famous. So the RC4 algorithm is not a difficult algorithm to understand, and it uses a variable length key from 1 to 256 bytes, and it uses it to initialize a 256 byte state vector S with elements from location 0 to 255. So at all times the set contains a permutation of all 8-bit numbers from 0 to 255. For encryption and decryption, a byte k is generated from the set S by selecting one of 255 entries in a systematic fashion. So as each of the value is generated, the entries of S are once again permuted. So this figure shows the working of the RC4 algorithm to generate a set of streams. So to begin with, the entries of set S are set to the values from 0 to 255 in ascending order. That is, at first location you will have the value of S0, and then S1, so on, S2, S3, up to S255. So then you can use a temporary vector T uh, if the length of key is 256 byte, which is equal to the S, then it is directly transferred to T. Otherwise, for a key length less than S, set will be taken from the K, and it will be copied to the set T. And then the K is repeated as many times as necessary to fill out T. Next, you will have the set T to produce the initial permutation of S. So this involves starting with the point S0 and going through the point S255. So for each location, swapping the value of location with another byte in S according to the scheme of dictated by the set described in T. So you pick two values from S and T and swap these values to generate the next set of values. For example, you take the value from set T and a value from the set S, and then calculate the new location for this value and swap the values of location I and J to produce the next initial permutation of S. Now it is important to consider here, because only the operation on the S is a swap operation, the only effect is the permutation. The S still contains all the numbers from 0 to 255. So once the S vector is initialized, the input key is no longer used. The key stream generation involves the cycling through all the elements uh, of S, and then each of the S swapping with another element of the S according to the scheme dictated by the current configuration. And when you reach the final value, the process continues over again from the location 0. And finally, to encrypt, the XOR operation is used with the value of K and the value of the plain text, and to decrypt, XOR is used with the value of K and the value of the cipher text. So there are a number of strengths of RC4 algorithm, and a number of papers have been published analyzing methods of attacking RC4. However, none of these approaches are practical against the RC4 with a reasonable key length. A more serious problem is that with the WEP protocol intended to provide confidentiality on the wireless networks which are currently used for LAN networks, however, these are vulnerable to a particular attack approach. The problem is not with the RC4 itself, but the way in which keys are generated for the use as input. Problem does not appear to be relevant to other applications and can be remedied with the WEP by changing the way in which the keys are generated. So problem points out the difficulty in designing a secure system that involves both cryptographic functions and protocols that make use of them. Another important consideration is the generation of true random number generators, that from where you generate these true random number generators, and these sources from where you generate the random numbers, numbers is referred as entropy sources. So our true random number generator use a non-deterministic source to produce the randomness. That means you use a source which is a diverse in the nature and it cannot be predicted by an attacker. So if it is a non-deterministic in nature, there is less chance that it will be guessed by the user, as it will have the high randomness. So most of these operators or random number generators operate by measuring unpredictable natural processes, such as you can measure the pulse of a person, or you can use the pulse detectors on ionizing radiation events. This is an example, or gas discharge in the tubes, or the leaky capacitors. So these are some examples of random number generators or random entropy sources. You can also use a simple temperature sensor to actually generate the random numbers. However, Intel has developed a commercially available chip that samples thermal noise by amplifying the voltage measured across the undriven resistors. So it is a good source of random number generators. So Lava Random is an open source project for creating truly random numbers using inexpensive cameras, open source code, and inexpensive hardware. The system uses a saturated CCD in a light tight can as a chaotic source to produce the seed. Software processes the result into true truly random numbers in a variety of formats. Additionally, you can use a number of other sources such as sound, audio, video, or disk drives. Our FC4086 standard lists the following possible sources of randomness and that can be used on a computer to generate the true random sequences. One example is using sound or video input. So in this case, the input from a sound digitizer with no source plugged in from a camera with the lens cap is essentially a thermal noise. So if the system has enough gain to detect anything such as input can provide the reasonable high quality of random bits. Or you can use the hard disk drives or other disk drives which have the small random fluctuation in their rotational speed due to the aquatic air turbulence. The addition of low-level disk seek time instrumentation produces a series of measurements that contain this randomness. Additionally, you can use an online service which is referred as random.org which can deliver the random sequences securely over the internet. So this table summarizes the principal differences between pseudo-random number generators and true random number generators. Pseudo-random number generators are very efficient, meaning they can produce many numbers in a short time. And these are deterministic, meaning that a given sequence of numbers can be reproduced at a later date if the starting point of sequence is known. Similarly, efficient is a nice characteristic if your application needs many numbers and determinism is handy if you need to replay same sequence of numbers again for a later stage. These numbers are also periodic in nature, which means that the sequence will eventually repeat itself. While the periodicity is hardly ever desirable characteristics, modern pseudo-random generators have a period that is so long that it can be ignored for most practical purposes. However, on the other hand, the true random number generation is very difficult process and these are rather inefficient as compared to the pseudo-random number generators, taking considerably longer time to produce the numbers. This presents a difficulty in many applications. For example, cryptography systems in banking or national security might need to generate millions of random number bits per second. Similarly, true random number generators are non-deterministic, meaning that any given sequence of numbers cannot be reproduced. It is a random event in the or a random phenomena in the nature. Although the same sequence may occur several times, such as as in the examples we have discussed, the same temperature can be observed during the days, different days, or in the even in the one day at a different time. But this is non-deterministic at what time that it will be discovered. Similarly, these numbers uh, may represent some periodicity. However, there is no fixed periodic period in these numbers. So generation of true random numbers is very difficult and it also is very inefficient. A true random number generator may produce an output that is biased in the some way, such as it can have more ones and then zeros or it can have more zeros than ones. So what is the term bias means in this concept? So NIST defines a random process as biased with respect to an assured discrete set of potential outcomes if some of these outcomes have greater probability of occurring than the others. So for example, if you are using an entropy source or physical source such as an electronic noise, which may contain a superposition of regular structures such as waves or other periodic phenomena which may appear to be random. In addition to bias, another concept used by the NIST is that of the entropy rate. So NIST defines the entropy rate as the rate which a digitized noise source provides the entropy. It is a measure of randomness or unpredictability of a bit string, and it will have the value of 0 when there is no entropy, that's no information gain or no difference between the information, and 1 with the full entropy. So conditioning algorithm or desqueuing algorithms are used to enhance these entropies. So for a hardware sources of random bits, the recommended approach is to assume that there may be a bias or an entropy of less than 1. So you can apply the techniques to further randomize the bits. Typically, conditioning is done by using a cryptographic algorithm to further scramble the random bits so that it eliminates the bias and increases the entropy. So the two most common approaches are used is hash functions and symmetric block ciphers. So operating system typically provide a built-in mechanism for hash functions. A hash function produces an n-bit output for an input of arbitrary length. A simple way to use a hash function for conditioning is as follows. So you can use a block of m input bits with m is greater than n are passed through the hash function, and the n output bits are used as random bits. To generate the stream of random bits, successive input blocks pass through the hash function to produce the successive hashed output blocks. So for example, the Linux uses 4 entropy sources: the mouse and the keyboard activity, the disk input-output operations, and the specific interrupts. So bits are generated from these 4 sources and combined in a pooled buffer. So when a random bits are needed, the appropriate number bits are read from the buffer and passed through a hash function to generate the desired random numbers. So this figure provides a general model for non-deterministic random bit generator. So a hardware noise source produces a true random output. So this is digitized to produce true or non-deterministic source of input. This bit source then passes through a conditioning module to mitigate the bias or maximize the entropy. This figure also shows the health testing module and an output. So conditioning and health testing modules are combined to produce the output. So health testing is used to validate that the noise source is working as expected, and the conditioning module is uh, used to produce the output with the desired characteristics. So here are some typical characteristics of health test and the noise sources. The nature of health testing on the noise source depends strongly on the technology used to produce the noise. So in general, the assumptions can be made that the digitized output of the noise source will exhibit some kind of bias or entropy rate. Therefore, traditional statistical tests are not useful for monitoring the noise source, because the noise source is likely to always fail. The test on the noise source need to be tailored to the expected statistical behavior of the correctly operating noise source. The goal is not to determine if the source is unbiased, but if it is operating as expected. So health tests are used to actually check the working of the true random number generator source, that it is working properly and it is not producing a biased input due to some error in the digitization of the noise produced by the entropy source. The NIST specifies that continuous tests to be done on digitized samples obtained from the noise sources. So the purpose of this test is for the variability and to determine the noise source is producing at an expected entropy rate. So NIST mandates use of two tests, repetition count test and adaptive proportion test. Repetition count test is designed to quickly detect catastrophic failure that causes the noise source to become stuck. It is simply to check that the noise source is working properly on a single output value for a long time, and it involves looking for consecutive identical cycles. So the repetition count test starts by recording the sample value and then counting the number of repetition of the same value. So if the counter reaches a cutoff value, that means it has read a number of values, that means the number of signals received in 1 minute great exceeds a specified threshold, then this test passes. So if sample value is encountered that is differs from the preceding sample, then the counter is reset to 1 and the algorithm starts over. The next test is adaptive proportion test, and it is designed to detect the large loss of entropy such as might occur as a result of some physical failure or environmental change affecting the noise source. That means your temperature sensor or other sensor may be placed on a location with alternate or uh, uh, or unnatural environments. So the test continuously measures the local frequency of occurrence of some sample value in the sequence of noise sources samples to determine if the sample occurs too frequently. So health test on the conditioning functions specified by the NIST specifies that the health test should also be applied to the output of the conditioning component, but does not indicate that which tests to use for the output. The purpose of health test on the conditioning component is to assure that the output behaves as a true random bit stream, and it is reasonable to use the test for the randomness defined in the NIST standard SP822. So Intel digital random number generators have been produced, and the true random number generators have been traditionally been used only for key generation and other applications where only a small number of random bits were required, because it is very difficult to generate the true random number generators. This is because this is also because the true random number generators have been generally been inefficient and with a low bit rate of random bit production. So the first commercially available true random number generator that achieves bit production rates comparable with the pseudo random number generator is the Intel digital random number generator offered on the new multi-core chips since May 2012, and it uses two notable aspects of deterministic random number generator. First of all, it is implemented entirely in the hardware. This provides a greater security than a facility that is provided only in a software component. So hardware only implementation should be able to achieve greater computation speed than a software module. Secondly, the entire deterministic random number generator is on the same multi-core chip as the processor. This eliminates the input-output delays found in other hardware random number generators. So this figure shows the overall structure of deterministic random number generator. The first stage of deterministic random number generator generates the random numbers from thermal noise, which can be an hardware entropy source. So the heart of the stage consists of the NOT gates and with inputs provided from the NOT gates or the inverters. So having NOT gates or inverters provide you a stable input or stable output having the logical 1 or the logical 0 as output. So the output of first stage is generated 512 bits at a time. To assure that the bit stream does not have a bias, a conditioning test is applied, which randomizes the input using a cryptographic function. So in this case, the function is referred as CBC AES MAC function, which is specified by the NIS SP838B. So in essence, this function encrypts the input using the Cipher block chaining CBC mode and outputs the final block. The output at this stage is generated 256 bits at a time, and it is intended to be have a true randomness with no bias. So while the hardware circuitry generates the random numbers from the thermal noise, it is much more likely that its predecessor is still not fast enough and some of today's computing requirements. So the output of pseudo-random generator numbers stage is available to each of the cores via the RD RAND instructions. RD-RAND instructions retrieve a 16, 32 or 64-bit random value and makes it available in the software accessible registers. So to conclude it, preliminary data from the pre-production samples on a system with a third generation Intel registered core trademark family processor produces the performance of up to 70 million RD-RAND instructions per second and the random data production rate over 4 gigabits per second. So this figure shows a simplified view of logical flow of Intel deterministic random generator. The heart of the hardware entropy source is a pair of inverters that feed each other. So two transistors driven by the same clock force the input and the output of both the inverters to the logical state 1. Because this is an unstable state, thermal noise will cause the configuration to settle randomly into a stable state with either node A at a logical 1 or node B with the logical 0, or vice versa. It can happen at node A with 0 and node B with 1. Therefore, the module generates the random bits at each clock rate. So the output of the entropy source is collected again in 512 bits at a time, and it is used to feed the two CBC hardware implementation using AES encryption algorithm. So each implementation takes two blocks of 128 bits. of plain text and encrypts using CBC mode. The output of second encryption is retained for the both CBC module and all zero key is used initially. Subsequently, the output of pseudo-random number generator stage is fed back to become the key of the conditional stage. So the output of the conditional stage consists of 256 bits, 128 bits of each. This block is provided as input to update the function of deterministic random bit generator. This update function is initialized with all the zero keys and the counter value of 0. The keys are 0 and the counter values are provided. The function is iterated twice to produce 256 block, which is then XORed with the input from the conditional module. The result is used as the 128-bit key and 128-bit seed value referred as C as in the last lecture. And this seed generates the next value which is fed to the again first module. So the generate function produces the pseudo random bits in the 128-bit blocks. This concludes today's lecture, and in this lecture we discussed about the working of stream ciphers and mainly focusing on the implementation of the RC4 algorithm. And finally we discussed some concepts about the true random number generators, that how these numbers are generated from the number of entropy sources, and what is the difference between the true random number generators and the pseudo random number generators. And there is a conditioning and health test, and finally we discussed an Intel digital number generator in the last two slides. If you have any questions, you can read the chapter number 8 of the recommended book, or you can ask me a question. Thank you very much.